Case study: Advancing Autonomous Robotics, Overcoming Challenges in Implementing Reinforcement Learning for Enhanced Efficiency and Interpretability. Reinforcement learning has revolutionized the approach to solving complex decision-making problems by enabling agents to learn from interactions within an environment. Picture a robotics lab where a team of engineers, led by Dr. Emily Norton, is focused on developing a sophisticated robotic arm capable of autonomously assembling intricate devices. The team's challenge lies in programming the arm to maximize the efficiency and accuracy of its assembly tasks using RL. Despite their expertise, the engineers face myriad challenges in implementing RL, including balancing exploration and exploitation, ensuring sample efficiency, and maintaining interpretability of the learned policies. To address these challenges, the team decides to model the robotic arm's environment as a Markov decision process. They identify the critical states, such as the arm's position, the components available for assembly, and the current stage of the assembly process. Actions include movements like picking up, placing, and rotating parts, while the reward function is designed to provide positive feedback for correct placements and penalize inaccuracies. A crucial question arises: how should the team design the reward function to guide the arm towards optimal performance without causing unintended behaviors? Dr. Norton proposes using Q-learning to model the arm's decision-making process. This model-free algorithm does not require prior knowledge of the environment's dynamics, making it ideal for their unpredictable assembly scenarios. The Q values, representing the expected utility of taking specific actions in given states, are updated iteratively using the Bellman equation. The team programs the robotic arm to follow the policy implied by these Q values. However, they soon encounter the challenge of exploration versus exploitation. How can the arm balance between trying known successful actions and exploring new strategies that might yield better results? To address this, the team implements an egg-greedy strategy where the arm occasionally selects a random action with probability ever and follows the best-known action with probability 1 ever. Dr. Norton's team adjusts EPTR dynamically, starting with high exploration and gradually shifting towards exploitation as the arm gains experience. This raises another critical question: what is the optimal strategy for balancing exploration and exploitation to ensure efficient learning without missing out on potentially better actions? As the arm begins to improve, the limitations of traditional Q-learning become apparent. The high-dimensional state action space of the assembly tasks makes it infeasible to store and update Q values using a tabular approach. To overcome this, the team turns to deep reinforcement learning, employing deep Q networks to approximate Q values using neural networks. This allows the arm to handle the complex visual inputs from its camera sensors and learn directly from raw pixel data. Yet, the engineers face another challenge: how to ensure the stability and convergence of DQN in such a high-dimensional and continuous environment. One solution involves using experience replay, where the arm stores its experiences in a buffer and samples random mini-batches to update the network, thereby breaking the correlation between consecutive experiences and improving learning stability. The team also employs target networks to stabilize the learning process. Two networks are used, one for generating target Q values and the other for training updates, reducing oscillations in Q value estimates. Realizing the potential for even more efficient learning, Dr. Norton suggests implementing actor-critic methods, which combine policy gradient techniques with value function estimation. The actor updates the policy directly, while the critic evaluates the action taken by estimating value functions. This dual approach can lead to more stable and efficient learning. The team now faces the question: how can actor-critic methods improve the arm's learning efficiency compared to using DQN alone? As the robotic arm progresses in its learning, the team realizes the importance of interpretability. In high-stakes applications like healthcare and finance, understanding the decision-making process is crucial for trust and accountability. How can they ensure that the learned policies are interpretable and transparent? Norton's team explores visualization techniques to map the arm's decision boundaries and uses surrogate models to approximate and explain the policy's behavior, providing insights into its decision-making process. Beyond the lab, reinforcement learning holds promise in other domains, such as cybersecurity. For instance, in intrusion detection systems, RL can be used to dynamically detect and respond to threats. Nguyen and Reddy highlight how RL can adapt to new attack patterns by learning from historical data, thereby enhancing the accuracy and responsiveness of security mechanisms. This poses a fascinating question. How can the principles of RL be applied to optimize resource allocation in cybersecurity, such as adjusting firewall rules or prioritizing response efforts based on evolving threats? Despite the successes, Dr. Norton's team acknowledges the challenges of sample efficiency. RL algorithms often require extensive interactions with the environment, making them impractical in real-world scenarios where data collection is costly or time-consuming. Techniques like experience replay and transfer learning, where knowledge from one task is transferred to another, are being explored to mitigate this issue. Another critical question emerges. How can transfer learning be effectively implemented in RL to leverage existing knowledge and reduce the need for extensive new data? Ethical considerations also play a pivotal role in the deployment of RL systems. Ensuring that RL agents act in ways that align with human values and societal norms is crucial. The autonomous nature of these agents raises concerns about unintended consequences and fairness. How can multidisciplinary efforts involving AI researchers, ethicists, and policymakers ensure that RL systems are fair, transparent, and aligned with societal values? In conclusion, Dr. Norton's team exemplifies the profound impact and challenges of applying reinforcement learning in real-world scenarios. The case study of the robotic arm underscores the importance of designing effective reward functions, balancing exploration and exploitation, leveraging deep learning techniques, and ensuring interpretability and ethical considerations. By addressing these questions and challenges, the team not only advances their specific project, but also contributes valuable insights to the broader field of reinforcement learning. The ongoing progress in RL holds the potential to revolutionize various domains, underscoring the importance of a comprehensive understanding of RL concepts for anyone engaged in AI research and application.